the semicircle of charge is nice because there is a little bit of calculus in it, just a little, enough to give you a flavor. But also the reason why I like to do the semicircle of charge is because the semicircle and the finite bar can't be done using a different law called Gauss's law. So you have to use this process for it. Therefore, two of these, of the three that we're talking about, have been on the AP exam. The infinite bar or a finite bar where you're one-dimensionally off to one side has been on the AP exam. And this curved bar has been on the AP exam dozens of times. Mostly because these are some of the only distributed charge ones that can be successfully done with the amount of mathematics and calculus we have, and that's just getting worse and worse. So perhaps. Yeah. Now I'm trying to draw this as a circular curve. I'm not sure how successful I was, but let's hope that it's kind of close to a circle. We'll see. That came pretty close to a circle. So I'll put the whole circle there just so we have reference. And let's say that the center of that circle is here. There are limits to the problems I can present to you. And this one has a limit. If we say that this is a charged bar of total charge Q, and that it is a total length, it is common to use a lowercase s as an arc length. That's a geometric term generally, is the arc length. So I'm going to use an s for the entire length of the arc. That's pretty common. But I want to specify something. There are some problems that can be done with the mathematics you have and some that can't. The problem we're going to do is placing a charged particle at the center. That problem can be done. We have the mathematical skill set to do it, even now. If I place that particle just randomly someplace, we can't do this problem anymore. The mathematics necessary are far more difficult and become almost impossible. The next possible place to do it is here on the other edge of the circle, because at least there is some geometric relationships between that point and the points on the arc, but they're not as nice as you would like. And if we choose this point, you have to understand that every piece of charge that we might select is not only a different distance, but a different angle from that point. And that might sound like it's like the infinite line or the finite line, but it's not, because the relationship is different for every single point. And the other one, the relationship was a right triangle. We don't have a right triangle here. That's an easy one to use to determine the distance between here and how that's related to the angle. There is a relationship, but you can probably imagine it's more complicated. So they can't ask just anything. They've got to ask something that's in the mathematical wheelhouse that you can successfully do. So they use simplified ideas, and they ask questions related to those ideas to see if you understand the nature. For example, we could spend a lot of time and come up with a solution for this problem, the force on charge lowercase q. And I would expect you, bless you, to perhaps know that if that charge were here, that force would probably be less. Right? We don't know it for sure because we can't necessarily prove it, but wouldn't you be able to reason out that it being further away from the charged bar would result in less force? And similarly, that the force would be greater over here. So they can ask qualitative questions, but the quantitative questions have to be within the wheelhouse of the skill set you have. So I know that, it feels like anything is possible. No, it's not. What is possible within our mathematics is very limited, which is why when I tend to show the exam, you end up seeing the same pictures over and over and over again across all the years of the exam. Lots of spheres, lots of straight lines, lots of cylinders, because these items have symmetry that can be exploited. So we're going to do this problem. And in doing this problem, I'll state it from the beginning. I would like the force on lowercase q due to the charged semicircle to the right. Not a semicircle, portion of a circle to the left. Let's state for the sake of this problem that the circle we're talking about has radius r. And also let's state that this circular piece of charge is centered on a line there. That's what I mean. That line goes through the center of the circle, and there's equal amounts of bar here and here. Is that okay? All right. So we would like to start this problem the same way we started all the other problems, and I'm going to help guide you through this a little bit, but I think I need you guys to kind of step up here. And look, body language says a lot. If you're struggling here, don't be a stranger about it. When I ask you to do something, please do it and do your best at it. And call me over if you're having trouble. I want you to start by perhaps finding a place on the bar. You choose your own place and call that a piece of charge. I don't have a place in mind, so I'm going to take that, this place right here, this little piece, and I'm going to call that my piece of charge, and I will label it dq. Now, you need to find a way to express how much charge there is in terms of the size of that piece. Now, I don't know if you can do this or not. Let's see if you can. We did something similar yesterday, and I'm just asking you to do the same thing as we did yesterday. All right, so did you set it equal to something? I mean, I would. I'd probably set it equal to something. Did you come up with remember it's going to be a density times a size. So, Jeremy, do you have a question, or do you want to try and tell me what to do? I did ask. That's why I'm asking. You want to tell me what to do? I wasn't trying to be facetious, sorry.
What I did Q over theta, where theta represents the total measure of the highest part of the arc to the lowest part of the arc from point Q.
Okay.
Is equal to dq over d theta.
Okay, so how many of you put it in terms of theta? Okay, that's a more limited number than I expected, but that's not unusual. Who put it in terms of ds? Okay, what else is left? So both of these are options. You could have just as easily said Q over S ds. That'd be okay. If I called the whole thing a piece of arc, I could call this arc length ds. That'd be okay. The problem is I have a fixed arc length S here. That's going to become confusing later when I try to integrate. So, but ds and S are almost always used for arc length. But there's other things we could have done. I think the idea of treating it like an angle is probably better. And there's a simple reason why. Every piece is the same distance away. Wouldn't you agree? That is a certain symmetry. And if every piece is the same distance away, no matter where I am along this range, the contribution to the force will be the same size. Right? Every piece is the same distance away, so every contribution to the force will be the same size. The only difference is that each contribution to the force will be a different angle at that point, but not a different size at that point. So, in fact, I think right now, if I was to connect these two and use that to indicate the direction of the force, would you agree there's a force in that direction from my piece dq? And the amount of this small contribution to the force would be equal to dq times q times k over r squared. Would that have to be true? Yep.
So you have said Q over, it can't be Q over L because it's an arc length.
It can be L if you call that length L. What we use here, or what the problem tells us here, isn't important. The bar has a certain length. Fair enough? Now, something I know that maybe you don't know is there's a relationship between the angle and the length of this bar. How many of you know that relationship? Okay, that should be all of you, and that's a little troublesome. So let's handle that. If I wanted, let's say I tell you that this length of the bar is S over 2. Can you write theta in terms of S over 2? If you can't, we have trouble. I'll have to teach that to you. That's a big water bottle. You better hydrate before you dehydrate. Now, if you don't know how to do this, I'm not trying to punish you, and I'm not trying to make you feel inferior. You learn this in elementary school. So, if I want to write this in terms of the angle instead, and there's good reason to do that, then I might want to replace this with something that has d theta in it, as opposed to ds in it. And I don't have to do very much. So I could write this as q over s r d theta. I know that I'm changing the order, but we know theta will eventually be at the outside edge of this. Now, I'm going to stop. Look, we are going to sum up eventually. So I can sum by going from negative s over 2 to positive s over 2. I could leave it in terms of ds. Fine. I could also say I'm going from negative theta to positive theta. I could do that too. That's just fine. I get to choose the variable of integration, so either one of these is fine. Right now, I see no reason to pick one over the other. I'm just saying there's other ways to do it. People talked about theta. People talked about ds. Okay, now we know different ways we could write this. Am I good to keep going? Because there's more to talk about. So is it yes or no? Because I want to make fun of this a lot, but I'm finding out I'm kind of a terrible person. So do you have a question to which you'd like me to respond or a comment? I would really like to respond to your question in kind.
So when you said S equals theta times R thing,
I'm not trying to I think maybe that's why people think I'm such a jerk. But I hate the idea that we learn things just to forget them later. The circumference of a circle is equal to an angle measure times its radius. The angle has to be the entire circle, so it's 2 pi. In this case, this is 2 pi radians. The definition of a circumference is based on the definition of an arc length. So the arc length would be equal to an angle measure times the radius. Going one step further, how big the piece of arc is also equal to a piece of angle times the radius. This might be where we're making a few mistakes and is worth kind of pursuing. So, I mean, clearly ds is just d theta times r.
That part confuses me a little bit because, I mean, the theta being radians or degrees in this case? Radians, right?
By definition, I don't want to say by definition is the wrong word. We generally don't have units here. However, radian isn't a unit. But I don't know if you know what radian is. It's a proportion, kind of, but yes, it is a proportion. Radian is defined here, and it's defined as circumference divided by radius. It's where the number comes from. So arguably, what a radian is a measure of the amount of a circle. It's not so that's why it's not a unit. It's the only thing in math and science where we say you have to be in radians and treat it like it's a unit and treat it like there are conversions where it's really not a unit. We have, this is a bit of an aside, but Celsius a unit. Is one better than the other?
Yes.
Now, interesting, I think the science-minded among us like to think Celsius is a better unit than Fahrenheit because Celsius has these rock-solid pinpoint locations on their little thingamajig that we know how to find, right? I freeze part of it, that's where 0 goes. I boil that water, and that's where 100 goes. And then I can divide it up into 100 even pieces. And I think science-minded people like that. Where'd Fahrenheit come from?
Arbitrary.
But it arguably isn't arbitrary. I mean, yes, it's arbitrary in the same way a foot was arbitrary at one time. But the Fahrenheit scale was meant to be the human scale, right? It's supposed to indicate the limits of tolerance of the human body. I don't think they're wrong. You go outside when it's 100, and I'll hear you complain. You go outside when it's 0, and I'll hear you complain. Exposure to 0 will eventually kill you. Exposure to 100 could eventually kill you. I'd argue the limits of the tolerance of the human body at 0 and 100 is not an unreasonable thing, providing you with a measured response for how we as humans behave around areas of hot and areas of cold. But you're right, it feels more arbitrary. It doesn't feel locked in place. And that's why water, boiling at 212 and water freezing at 32 feels like, wow, they just kind of picked something arbitrary out of the system. They didn't. They didn't have the technology, nor really the understanding of temperature before that. And being that it's been kind of warm and kind of cold here on campus at various times these last couple of days, it's kind of funny. Because I would argue that most of you found the room to be quite cool when you walked in off the street just a few minutes ago. And then probably later today, you would say it's kind of warm when compared to other states that you will be in. So temperature's a tough one, but we do have this rooted idea in there. Fahrenheit feels arbitrary. Celsius feels based on something. Do we have the same thing here for radians and degrees?
Yes.
Does anybody know what the degree is based on? It's a good number. 360 is a good number. Of all the numbers we could have, big fan of 360.
360, it's divisible by 3, it's divisible by 4, it's divisible by 5.
I like it. It's a good number. Have it on my tombstone. Yeah, which might be coming at me pretty quick. Yeah, go ahead. I could say yes, but that would be minimizing it a little bit. It's navigational. 360 works because circles and 360s go together really well. I mean, that's also why, do you know why degrees are broken up into minutes and seconds? Yeah, rotation of the earth. Minutes and seconds appear in there because of that. We based it on something that felt appropriate at the time. And that would be circles and the rotation of the earth. That's why a sextant works the way it does in helping you navigate. Now, I'm not being arbitrary. There seems to be points about degrees that have real meaning, maybe more so than Fahrenheit. But how many of you heard that there's other ways? Truckers know a third way to measure angles. I know you tend to not think of that, but truckers do. Truckers know. You know what it's called?
I wanted to say stars.
There's gradients. I don't know if that's the right.
The gradient of a road is the angle measure of a road. It's a percentage. 100% would be straight up and down. It'd be a wall. Right? You could measure a gradient based on the percentage of inclination. Why not? That feels very particular, right? Feels very rooted in science. 0% perfectly level, 100% perfectly 90 degrees. Oh, wait, there we go, 90 degrees. Why 90 and not 100? You understand? The gradient makes perfect sense too. So clearly this is not falling the way I'd like it to, but I'd argue that 2 pi feels like it makes no sense, even though it's the one most rooted in a circle. But it's just the ratio. What do you mean? I'm sorry, somebody asked a question. I didn't hear what they said completely. Oh, pi is just a ratio. It's a ratio of the circumference to the radius of a circle. That's all it is. But because of that, half a circumference would be half of that ratio. So we have figured out that we could use that ratio in a manner to be an angle measure. It didn't have to be. But we have figured out that half that ratio would be pi. Well, we could probably associate an angle with that. I'd argue that the angle measure in radians is the least connected to the reality of what a circle is like, but is completely rooted in a circle. Well,